Yes, we're gonna move to the section we stopped at, and this was dealing with logarithms. It was section 4.2, right? So we worked on the, I think we had a little quiz exercise. Let me try to find it here. Was it a quiz or I have created something? I think I probably created some kind of question for you, because I don't think I see it here. So what was it, like logarithm base 3 of, I don't remember, 27, something like that. So if you remember what it was, please remind me. But anyways, just to start, logarithm is a power that I need to raise base to get 27. So that's the definition of logarithm. It's just another way to write the exponential statement, and power is 3 because 3 cubed is 27, so is the logarithm. So that's one of the ways to do the problem. The other way is to use change of base formula. You can write ln over ln and put it in the calculator. So 27 goes on the top and 3 goes on the bottom. So now I can take a scientific calculator. So just start typing scientific and it pops up. So we select this first choice, right? And then I need to find ln. So since you don't see ln, you go to functions, right? So main, and then there's functions. And then among functions, you will be able to see ln. So you use this little symbol. So ln of 27. So I go back to main menu, 27 parentheses divided by another ln. So again, functions, and then choose this ln and then put number 3, right? Like that. Yeah, you can see that you can do this just using a calculator, but you need to use a change of base formula, so it's also requires a little bit of knowledge of work with logarithms, but they're just powers. That's all one needs to realize. So there are various little exercises here that want you to manipulate with these logarithms and use them to solve various little equations and simplifying things. I hope you already encountered logarithms prior, so I can do, say, exercise 24 in this section that has a 3 raised to some power, and that power has letter x. That's the one that I need to find, and this is equal to 17. So since 3 and 17 are not really friends, then you get ln to apply on both sides, because this way you can bring your power with x in front. So this will be 2x minus 1 multiplied by ln of 3, and this is equal to ln 17. So first of all, I put x on the ground. The next step will be to distribute. So little by little, we're going to solve equation with respect to our unknown letter x. So when I distribute, now I need to bring this everything to the right side, a little by little. So first of all, I'm gonna minus that ln 3. ln 3 is just the number. So minus ln 3, I need to add so it appears on the right side. Like that. So we get that result with a 2x times that ln of 3 is equal to a difference, sum of two logarithms. You can put them as a ln of 17 times 3 or 51, but it's not as important because we've got the answer here. So this fraction gives us what we need. It gives us x. And then if you wish, you can always put this in a calculator, or if you wish to make it look more compact, up to you if you want to play with these logarithms. But for purposes of this class, I think that's good enough. Now, how about if you have e present here? Well, we had a formula that said logarithm of base e and the exponent of same base e, they will disappear. In other words, if I'm gonna apply ln to both sides, then we're gonna get a x on the right side right away, and that's what we really are after. So standard approach. So you apply ln, and this way you're gonna get just 0.06x on the right side, which is equal to ln2. And then it's time to divide by 0.06, right? So I divide both sides by that, 0.06, and we got ourselves a nice result. We got ourselves the x, and whatever it is, again, I just keep it like that. So this is our solutions for these little exercises, and I guess that's the way to go. So we solved another equation. It looks like these things are what we practiced already, and I'm gonna move on because we actually should be doing some calculus rather than playing with logarithms, because this is really intermediate algebra. And here's the start for derivative of e to the power of x. I like to put it with a prime, so it's same e to the power of x. Remember, they could write this derivatives with d dx, and that's the same as a derivative anyways. So they give you the formula, and we're gonna utilize this formula to, I guess, get various exercises solved. There is one more formula here that says derivative of natural logarithm of x is just 1/x. So this is another little formula that they provide us with in this new section. So we're going to do derivatives, and then we're going to see what we can actually utilize these derivatives for. So let me start out with, I guess, practicing. So here's the section. There's a number of little exercises that I hope you're gonna like, because I think that these derivatives for logarithms are pretty straightforward. In fact, we already learned how to do derivatives, right? We had this on the midterm, and you really impressed me, so you know how to differentiate. And now we get a couple of more little formulas in addition to what we learned. So let me do problem number 2 that says take a derivative of 3 times e to the power of 4x plus 1. So if I have to take derivative of this kind of function, then 3 will stay because that's a factor. Now I will use the formula derivative of e to the power of x, which is exactly the same thing. So that's my favorite formula, actually. So you just write e to the power of 4x plus 1. But there is so-called chain rule, remember? Because power of e is not just x, it's 4x plus 1. So you need to multiply it by derivative of 4x plus 1, which is 4. And of course, this 3 times 4, I'm sure you can put together is 12, right? So it'd be nice to get the answer is 12 times whatever e power of 4x plus 1. So besides using the new formula, we also recalled our favorite chain rule, and that was used a lot. There are also properties for derivatives of product and quotient that this section will expect you to use. So it's f prime g plus g prime f. Remember that formula? Derivative of product. Not favorite, but I guess in the exercise, like say 36, you have to use it. Actually, I don't want to do this exercise today. I'll do it next time. So, recordings. I updated the YouTube channel, and I'm glad you noticed this. It takes a while, so it makes no sense for me to upload one recording and then next day another recording, next day the third recording. So I wait for a few of them, maybe a couple of weeks or so, and then I will upload everything after that, because it's really time-consuming process, at least for me. And that's why, because you need to have internet signals, so there are various things involved there. So anyways, but I will upload it, but not today or tomorrow. It's in a couple of weeks. But today, later, I will be emailing you a link to this recording, so you can just watch it if you want to through the regular Zoom. But I will, of course, because I updated the YouTube channel, so I think I put the lectures, pretty much everything up to the last one that we had on Wednesday. Not sure if I put Wednesday's lecture or not, but everything is there. So I hope it's convenient, and I mark them as 1, 2, 3. They may be a little bit mixed up because I need to see how I can rearrange those normal way. But so far, yeah, everything is on YouTube, and these new lectures related to the new chapter will be there eventually. So let me concentrate on the previous stuff, because I don't want to do 36 as of yet, because there'll be another formulas. I think for us enough for today just to deal with these two. I don't want to throw on you more formulas. It'd be a little bit too much, I think. So let me just stay away from it, and maybe do the exercise like number 3, which is much nicer, because it deals with e to the power of x only. So it says, how about if your function is x times e to the power of x? Can you find the derivative of that function? Well, I'm gonna break this into pieces f and g. So f is multiplied by g. And now I need to know the ingredients, such as f prime and g prime. So I'm gonna be using that formula above. So f prime is 1. And g prime, well, that's derivative of e to the x. That's my favorite formula. It's the same e to the x. So using this pieces, I'm gonna now set up this big sum. So it's f prime, which is 1 times g, and g is my e to the x function, plus g prime, which is also e to the x, and it's multiplied by function f, which is x. Just like that. When you say, should I factor e to the x out? You don't need to factor. Nobody told you to factor. So you found derivative, you can just leave it like that. That's good enough. It depends what you asked in the exercise. If just find derivative, I think that's enough. But if you asked to graph or do something with it, well, then you're gonna do various other things. But I think for now it's good. So let me try ln, like say exercise 13, that says take derivative of ln of x cubed. So we're gonna have to use the favorite chain rule once again. So now we're gonna use a new formula here because of ln that has a special derivative 1 over whatever we have with ln happens to be x cubed. And then we times this by derivative of x cubed itself, and x cubed will have derivative 3x power of 1 less 3x squared. So then I'm going to be canceling x squared. So 3 will stay on the top and x on the bottom. Well, I guess here is not very hard to see that you can cancel, right? Because x cubed is x times x squared. So you can just get rid of x squared, and whatever's left, x will be on the bottom and 3 will be on the top. So I think that's not very bad formula, so you could definitely utilize it. And I guess our goal for today to get used to these formulas, so I'm gonna do number 17, just play with them a little bit, because till the rest of this chapter, we're gonna work with ln's and e to the powers. So how about ln of x cubed? Let me take this derivative. So looks like I need to flip, right? Put 1 over x cubed. That's first step. You say, why'd you flip it? Well, here it is. Here's the formula. That's a new formula. That's something that we need to look at. See, that's new information. Whenever you have a ln, take derivative. Whatever with a ln, you put in denominator. And then I think I'm doing the same exercise again, or what? ln x cubed. Oh yeah, 17 is not that. I'm sorry, it's same thing. Again, looks like it's my favorite problem for today, right? Not sure why I do exact same one. But anyways, we just done it, right? So let me try actual 17. I wanted to do 17, but selected different problem by accident. So in the problem number 17, it's e to the power. Now, I have the power here, which is a cube root, which is 1/3, right? Please notice that the property of exponent says, Alex, you can multiply 2x by 1/3 because power is raised to the power. So I can do a little bit of simplifying. So e will be raised to the power of 2/3, right? 2 times 1/3 is 2/3 times x. And now I'm going to take a derivative of that stuff because now it's more straightforward. Now, in fact, my favorite formula comes into play, right? Derivative of e to the whatever power will be the same, e to that 2/3 x power. But then I need to multiply this because of chain rule by derivative of that power. So what's the power? Well, it's 2/3 times x. So we just end up with 2/3 and x has derivative of 1. So we just leave it like that. So the point is, these radicals, you don't need them. Just put them as fractional powers, and that will be it. Analogously with problem 12, I'd rather write this as e to the power of 1 over x, and that's x to the negative first. Again, I want to have powers because we have formula for derivative of powers. Because otherwise, if you tried to find the derivative of 1 over x, which is a power of e, you would have to use that f prime g. Remember, derivative of quotient. That's the last thing I want to ever use. But sometimes you have no choice. But looks like in this particular exercise, I can take a derivative of this. So e to the x will stay the way it is, e to the x to the power of -1 or 1 over x, whatever you like, times, and now you take a derivative of that power itself. And when I take derivative of that power, -1 will be multiplied by x to the power of -2. Why is that -2? Remember the power rules. For derivatives, you need to subtract 1, right? And I guess this one could be definitely improved a little bit, right? So you can write this e to the power of 1 over x, and the minus sign will be in front, and that x will be in denominator as x squared. So I hope you can see this. So the point of story is it's faster rather than using this derivative of quotient to avoid it. Well, just make life easier. But in the exercise like number 4, there is no way around. In the exercise like number 4, you have to use that formula. So let me put it in red so we can see the resemblance. So in this problem, I have e to the x on the top and x is on the bottom. So there's nothing I can do. So to find derivative, I have to use the formula for derivative of quotient. And that's why I'm going to call functions f as my numerator and denominator as function g, right? And then I need to take their little derivatives, and then I will be able to set my fraction. So derivative of x is 1, that's my favorite. Derivative of e to the x is another favorite, it's same thing. So let us go ahead and produce this structure. So my denominator is squared. Now there'll be a difference on the top of f prime times g. So try to write it down. It's not hard. I'm sure if you do it once, then you will always be able to do this. So f prime e to the x multiplied by function g, which is my denominator, right? Minus, now g prime, that's 1. That's nice. Times function f, which is e to the x. So I will leave it like that, because even some people say, Alex, I like to factor. I just really into factor. Well, you can try, but it's not going to give you anything. Yeah, it's going to look a little bit more compact, but again, depending on the purpose of why you're doing this exercise, sometimes it's better to leave it like that. But you see, the derivatives become pretty tedious when you start using this quotient rule. But there is no way around. That's the only way to actually do this. So those are things that we see here in the chapter 4. So we're going to work with this little derivatives here. I can check and see what else is in section 4.3. Again, there are some exercises that expect us to use a little different formulas, and that's why I think I will rather utilize it next time. I just want you to get used to this first, and then we'll move on to the next. So you can see there are more and more exercises on this page, so you don't have to worry much about all of them, because that's, well, just more and more of these same things using the same formulas. We didn't do for a while any equations of lines, so I want to do one here. So let me try something like, say, problem number 52 that says, find the equation of tangent line. Remember what we used to do before? We have a function here, which is a difference of x and ln x. So if you imagine yourself this kind of graph, it might be something, who knows. Now there is a point E someplace. So on the x-axis, there's point E. And what you want to do, find the equation of tangent line at that point E. So you need a slope of line, and then you have a point, so you're going to be able to actually put this E in. So it's going to be E minus ln of E. You know what ln of E is? 1. So that's my y coordinate of this point. So one coordinate is E and the other is E minus 1. E is 2.7, so it's like 1.7. So at that point, I need to get an equation of tangent line. And to be able to do it, I need a slope. So I take a derivative of my function. And derivative will be derivative of x is 1 minus 1 over x, right? And then I have to plug again this E, but in derivative. So this way I get that slope. Okay, so whatever it is, 1 minus 1 over E. You see that E is everywhere. Well, it's 2.7. So you can technically put this in a calculator and get yourself the answer. But yeah, it doesn't look very natural, right? It's kind of something that you don't see too often. But we will see it in this class. We will see this in the next chapter when we're going to look for anti-derivatives. So we'll encounter this number E again. So now I'm going to need to use the, so that's x1, and that's y1. So I'm using equation of line, and I need to plug into it x1 and y1. So I'm going to subtract from my y coordinate whatever is called y1, which is E minus 1. So I just utilizing the equation of line. So now instead of slope m, I have derivative here. It's 1 minus 1 over E at that point. It looks kind of unpleasant, right? And then I multiply it by x minus x1. Well, at least x1 looks nice, by x minus E. So this is equation of line. It has x and y, but this number E is definitely not very nice looking, right? One can say, Alex, maybe you can simplify this equation. Yeah, I can do this, but I just need room for that. Maybe I continue on the right side. But again, that's equation of line, so technically you're done, right? But of course, if you feel like simplifying, you can always do this. I'm not gonna pick on you if you don't simplify, because I know it's already algebra, not a calculus, so some people may not feel good about this. So first of all, I'm going to get rid of the parentheses. So same here, so I'm gonna have to multiply by 1 both of those. So by 1 is my favorite multiplication, so you get the same thing, x minus E. And then I'm going to need to multiply both of those by 1 over E, right? Okay, so let us also do that. So it'll be minus 1 over E times x. I don't think it really brings you somewhere in a better position. That's why I don't think there is a point to multiply. And then there will be plus 1. Notice that if I multiply this 1 over E by E, E will cancel, get plus 1. So what else happens here? Minus E and minus E cancel, plus 1 and plus 1 cancel. Oh, actually, it's nicer here. So y is going to be equal to x and 1 over E times x. So sometimes people factor this out. So get 1 minus 1 over E times x. Like that. But again, there's parentheses, so that's your slope, right? So that's the answer. Is it much better than the original? I'm not sure. So you can just leave the one that we had here without any change. So I guess maybe a good time for you to try to find derivative, and I saved a special one for you for a quiz. It's exercise number 1. I'm sure you're gonna like that, exercise number 1 for today's quiz. So please do this as usual in a Zoom chat and just put your answer in it. And it's a pretty straightforward application of our new formula, the one that I really love. So that's our quiz for today. Again, I just want to remind you all that I'm still waiting for some people's homework and even for some people's